Hello, Stats 300, and this is Professor Gonzalez, and I'm taking a look at homework problems on the assignment side of ALEKS, section 9.4, which is looking at the hypothesis test about a proportion. So I think we need to talk about proportions a little bit. So I took a picture, or actually took some notes on notation, so I wanted you to see that at the bottom of this. Notation. Okay, so we use the following notation. P, little p, represents the population proportion of individuals who are in a specified category. So, for instance, if I want to know the population proportion for people who wear glasses in the world, it'd be a very hard number to get to, right? You would have to go out and talk to all 7 billion people in the world, and then let's say you interviewed them and 3.5 of them, 3.5 billion people claimed or told you that they wear glasses. So even though there are a lot of those numbers are super large, it is a proportion which can reduce down or can be written as a decimal. And 3.5 is exactly half of 7, so 3.5 billion divided by 7 can be written as a decimal value, 0.5 or 0.50, or as a percent, or as a percent, which would be 50%. So, if you saw in a problem that was talking about proportions and things like that, and they said, the population proportion, or they said something about 50%, that could be thought of as a proportion, right? Where P would be 0.5, okay, or 0.50. Anyhow, we also have something, so finding that population proportion is often a difficult thing to do because that population can be very large, like the population of the world. Probably the next best thing would be to find p hat. Now, p hat is the sample proportion, so it's still a proportion, but it's of the sample. And how do you come up with the sample proportion? Well, the sample proportion is going to be equal to, let's start off with the sample size, right? The size of the sample, and that's the denominator, the total people in the sample. And what is the numerator? The numerator is going to be x, which is the number of individuals in the sample who are in the specified category. So in my example, instead of interviewing 7 billion people in the world, let's say I made a simple random sample of, let's say, 200 people, and it turned out, I talked to 200 people, and it turned out, let's say 105 of them wore glasses. Okay, so we wouldn't exactly expect our sample size to be our sample proportion rather, would be exactly like the population proportion. But we're hoping it's kind of close, and we have some statistics to try to figure out what that population proportion is, or doing hypothesis testing or confidence intervals, things like that. Okay, so there's the notation. Let's take a look at problem number 1 and see if we can answer that question now that we know some of the proper notation. In a simple random sample size, so this is sample size, and I used green before, so I'll continue with that. That's n. There were 37 individuals in the category of interest. Well, 37 are the people that claimed that they were, like in my example, people that wore glasses, so that would be the x value. So if we want to find p hat, if we want to figure out what p hat is, which is compute the sample proportion, that's just going to be, remember what we said before, that's just going to be x over n. So let me go just back to one color. So the sample proportion is going to be x, which is 37, divided by n, which is 62. Round your answer to at least 3 decimal places. So we round to 3 decimal places. And that gives us, let me write it like this, sample proportion is approximately 0.597. Okay, then it says, are the assumptions of the hypothesis test satisfied? Well, I have some notes for the assumptions. And here are the assumptions. It says the method for performing hypothesis tests about a population proportion requires that the sampling distribution be approximately normal. So these following assumptions, if these assumptions are satisfied, then we can be sure that our population proportion is the sampling distribution will be approximately normal. And then once it's normal, of course, we could use t distributions, z-scores, all these different things that work on normal distributions. First of all, number one, we have a simple random sample, okay? Number two, the population is at least 20 times as large as the sample. So if you take the sample size times 20, that better be, let's see, the population is at least 20 times as large. So sample times 20 is going to be smaller than the population or equal to the population. So the population is at least 20 times the sample, at least. So the population could be much larger also, but it has to be at least. The items in the population are divided into two categories. So let's talk about that. So in my example, you're going to see in the second part of this question, it's still question number one. The population proportion of the problem is actually 0.7 or 70%. So the two different categories here are going to be, okay, so in my example, the two categories would be people that wear glasses and people that don't wear glasses. In this problem, I'm not sure, I don't think they specify because they're just getting us to get used to this notation, first of all. But the two different categories, two different groups would be this population proportion is 0.7, and the other one is just going to be 1 minus 0.7, which ends up giving us 0.3. So you could actually figure out how many people are in those populations by multiplying it by the sample size, right? How many people are in this grouping? Well, 70% of them are. And how many people are going to be in this grouping? 30% of the sample are going to be. And so basically what they're saying is both of these groups, let's say group number 1 and group number 2, because there's only going to be two groups, are both at least 10, okay? The number of people in that group must be at least 10. Let's go back to our question, see if we can answer that question now. And it says, here we are right here. Are the assumptions satisfied? Okay, well, let's see. Let me get my color here. The first one we're going to look at is, it's going to say n. Now we know n in our sample up there was 62. Sample size was 62. And what that assumption that we just were looking at, it says n times the population proportion. And when we have that little sub-zero right there, that basically just means our population proportion from our H naught or our null hypothesis. So that's the guy we're talking about. That is our population proportion from the null, which is 0.7. So we're going to use that. Whoops. It's 0.7. And we take a look at that. When we multiply those two numbers, we get about 43.4. And that is greater than or equal to 10. So that is at least 10. So that's satisfied. And the other one we need to look at comes from, remember, P. So it's going to be 1 minus P naught. And 1 minus 0.7 is going to give us 0.3. Of course, we also need to multiply that by our n value, which was 62, our sample size was 62. And when we multiply 62 times 0.3, we get approximately 18.6, and that's also greater than 10, or at least 10, I should say. So we're going to say, are the assumptions satisfied? Yes. The number of individuals in each category, right? The first category and the first category and the second category is greater than 10. Okay. On to the next question. It is desired to test our null hypothesis, meaning the population proportion is 0.7 versus our alternate hypothesis, our population is not equal to 0.7. Compute the test statistic z, round the answer to the nearest two decimal places. Now we know it's a z statistic because when we go take a look at our formula sheet that we always go back to, this is section 9.4, and notice this is test statistic for a population proportion, for a proportion. And so there's the notation for that. That's our formula for this section to figure out what the test statistic is. Basically what it is doing is it's taking our sample proportion and turning it into a z-score, essentially. Okay, so let's take a look. And then once it's a z-score, then we put on the standard normal, and we can do all these great things that we've been doing with the standard normal curve. So let's go back up here. See, here it is right here. So I'm going to go ahead and write that again just so we get used to seeing that. It's going to be p hat minus the population proportion from the null statement. And that is going to be all divided by the square root of what? The population from the null times its complement, all divided by the sample size. So what does this look like? Well, we've got our p hat, right, which is right here, right, our sample proportion. So that sample proportion is 0.597 minus our population proportion from the null. We already saw that right here. That's 0.7. That is divided by population from the null, which is 0.7, times its complement, which is 0.3, right? 1 minus 0.7. That gets divided by a sample size of 62, and the whole thing is square rooted before we divide. So then we do the math. Up top we get negative 0.103. Down below we get approximately 0.05819867695, and so on. So we divide that and we get z is approximately negative 1.769796. It says please round to the nearest two decimal places. So we're going to say z is approximately equal to negative 1.77. And that's our answer. That is our test statistic that comes from our sample, right? So that's not going to be that's going to be what we plot and figure out if that's too far away from our population proportion or too far away from the zero, or on the z table, 0. If it's too far away, meaning it goes past our criteria, which the criteria is set by our alpha. Let's see, here it is right here. Then we're going to reject. I'll draw a picture. Okay, so let's find the critical value or values. So now we go back here, right? How do we figure out what type of test we're going to do? And we always look at the alternate hypothesis. Now, when you see this symbol not equal to, we know that that's going to be two-tailed. A two-tailed test. I think I'm going to put some of that information right here. Yeah, this would be a great place to put it. So it's a two-tailed test. Now, the nice thing about this section is we're talking z-scores, right? And finding critical values for z-scores is really easy because we've got a chart. Now we're looking for 0.0, alpha is 0.01, and it's a two-tailed test. So we can figure out those critical values. We could look at our z-table, but better yet, we can look at my note page at the very bottom. There it is, critical values for z-scores. And we want, let me get some color here, we want a two-tailed z-score. And what was the actual alpha level? Significance level of 0.01, which is way out here, which means those are our critical z-scores. Plus or minus 2.576. So we got a negative 2.576. We got a positive 2.576. And essentially, let me draw a little picture. When we plot our test statistic, if we end up in this region, we reject. If we end up in this region, we reject. Remember the standard normal curve, that's 0. If we end up in this region, when we plot our test statistic, we do not reject. Let's plot the test statistic. Okay, what was our test statistic? It was, go back up here, here it is right here. So our value, right, the test statistic is negative 1.77. Well, negative 1.7 is somewhere in here. Maybe that's not perfect, but you know what? It's good enough because I definitely know that it is not into that red reject zone. So this is z is approximately equal to negative 1.77, which means we do not reject. So critical values, they asked for that first. Let's write that down. Critical values, that happened to be plus or minus 2.576. Do you reject HO at a 0.01 level of significance? And the answer is no, we do not reject it. No, we do not reject it because you can see we landed right there in the do not reject region. All right, let's take a look at our second of 3 questions. So this is actual full-blown. This was basically kind of getting used to the different notation and stuff like that. Let's do the problem now. So this particular problem, we take a look at this. I'm just going through the different steps they have for us. Let's just answer the questions. A marketing manager for a cell phone company claims that the percentage of children age 8 through 12 who have cell phones differ from 51. Okay. So, and then at the very end, let's see, the question is, can you conclude the manager's claim to be true? What's the manager's claim? Let's see, a marketing manager for a cell phone company claims that the percentage of children aged 8 to 12 who have cell phones differ. So it doesn't say greater than, it doesn't say less than, it says differ, which that means, so their claim here would be it differs from 51. it differs from 51. And we know that the null statement is always going to have equals. So this is going to be P equals 0.51. And the claim is we want to know, can we conclude the manager's claim is that it's different from 51%. Okay, so that sets that up. Now what comes next is a survey, right? In a survey of 839 children, that's going to be our n value, right? Survey is 830 children, ages 8 through 12 by a national consumers group. 415 of them had cell phones. Okay, well that's going to be our X, right? Out of 830, 415 of them had cell phones. That is the specified group. So 415 of them had cell phones, so that's the group that had them. So that means our population proportion, P hat, right? That just is going to be figured by taking our X, people that had cell phones, the kids 8 through 12 that had cell phones, over the total kids 8 through 12 in the sampling group. And when we divide that, and we get, actually we get exactly, and that's exactly equal to 0.5. Okay, so we have our P hat is 0.5. Some assumptions that we really, they're not asking in this particular problem, but really supposed to be looking at those assumptions. I think I'm going to write those down. It's really good practice here. What are those assumptions? Well, remember the assumptions would be that n times our population from the null must be greater than or equal. It's at least 10, so let's just greater than 10. Okay, so sample size was 830. Our population proportion from the null was 0.51. And when I multiply that, yeah, that's over half. That's going to definitely be bigger than 10. Okay, and then the other one was, right, what's the other group or other category? That's just 1 minus P sub 0, or population from the null, which was 51%. So 1 minus 51%. So that's going to be sample size was 830. 1 minus 0.51 leaves me with 0.49. And that's still close to half of those people, which is way bigger than 10. So anyhow, they didn't really ask for that, but those are the assumptions that are supposed to be met to make sure that we are working with a standard normal, or the distribution is a normal, approximately normal. Okay, let's take a look next. Find the critical values around the answers to 3 decimal places. Okay, so finding the critical value for something like, something that has an alpha, right, level of significance of 0.05. Now, when we take a look at this, we need to determine what kind of test are we talking about, and we can see by taking a look at the alternate hypothesis is not equal, so that means two-tailed test. So the beautiful thing about this is with this particular section, remember our test statistic is talking about z-scores, right there, z-scores, right? Oops. Come on, z-scores. And so the easiest way to do this is to take a look at that nice handy dandy chart that is on our note card. So let's go here and get rid of some of that old stuff. And let's check it out. Remember, it was a two-tailed test, so we're taking a look at two-tailed. And I believe the alpha, or the level of significance, is 0.05. 0.05 there. So that means our critical values are going to be plus or minus 1.96. So this is going to be plus or minus negative. So it's going to, we got negative 1.96, and the other one is positive 1.96. Those are our critical values. Okay, let's continue on, see if we could answer this question. The next piece is asking for compute the test statistic. Do not round intermediate calculations, right? Keep those decimals as long as you can through the calculator, and then round at the very end to 2 decimal places. Just as a reminder of what that formula is again, remember our formula is going to be p hat minus, which is the sample proportion, sample proportion minus the population proportion, which is from the null statement. And then we have the square root of the population proportion times its complement divided by the sample size. Okay, let's see what we got here. So putting in all these values, we've got 0.50, which was that sample proportion, and then we got the population proportion, 0.51. So then we've got our population proportion, which is 0.51, times its complement, which is 0.49, divided by the sample size, which was 830, and you got to take the square root of that. So now when you take a look at this, up top we get a negative 0.01. Down below we get approximately 0.01. And this is where they don't want us to round. 7351782, depending on how many decimal places your calculator rounds to or can display. 0.57630968, and that goes on. So we round to 2 decimal places, and we're going to get our z rounded to 2 decimal places. That's going to be, that's going to be a negative 0.58. That is always good to remember that this is our test statistic, our z value that came from our sampling data. So this represents what we're looking for, and that's what we got to plot to figure out if we need to accept or rather reject or do not reject. So I think a picture right now would be a great thing to have. And I probably should have had a little more space. I'm going to squeeze that picture right in here. And we said that this is going to be two-tailed. And we already figured out that our critical values from our previous question are going to be negative 1.96. So this is negative 1.96. And this critical value is positive 1.96. The big question is, let me go back to this. This, of course, wrong color. This is our 0. And we expect our sampling data to be close to our population proportion, which would be at 0, which would represent 0 on our standard normal curve. And so the further away from this, the more we disagree that population proportion is actually true, right? In this case, in this particular problem, it was a two-tailed test, and if you end up in this red region, we must reject. We must reject the null statement, HO, or H sub 0, or H naught. Reject. Now, if we end up plotting in here, this means do not reject. Reject what? Do not reject HO, right? The null statement. Okay, well now we know that our test statistic came up with this number. Let's plot it and see where it goes. Negative 0.58. Negative 0.58. Well, that's somewhere in here. And that is in my do not reject region. Do not reject region. For some reason, it doesn't write. Yeah, in my do not reject region. So let's answer the question. At the alpha level of 0.05 level, do not reject the null hypothesis. So this is do not reject the null hypothesis, right? Because it's not that far away from the not that far away from the null hypothesis, which was the population proportion. It's not that far. By chance, it could be there, so we're not going to reject. If it was way out here into this red region, that's more than by chance in our opinion, and we are going to reject that null hypothesis. It says the population proportion should be right here. Okay. All right. State the conclusion. Okay. Well, if you do not reject the null statement, then our conclusion statement is really wishy-washy and wimpy, really. At the alpha level, or at the alpha equal to 0.05 level of significance, there is not enough evidence to conclude that the percentage of children age 8 to 12 have cell phones different from 51. Now remember, maybe it's a good idea to restate the null here so you can kind of see what just got it right in front of us. Remember the null said, what did it say? I got to go back and look at it. I believe it said that the population is going to be equal to 51%. And the challenger, the alternate hypothesis, said that the population proportion differs, so it means it doesn't equal 0.51. That's what that said. Okay, so now we come through with all this great information after we did our test statistic and analysis, and it turns out that the test statistic or our information from the sampling data end up putting us not that far off of the null, so we cannot reject the null. So if we rejected the null, this guy, then we would clearly say this. We would say it differs, but because we didn't reject it, right? There is not enough evidence to conclude this, right? There's not enough evidence to conclude that ages 8 through 12 who have cell phones differ from 51%. We cannot conclude that because we did not reject the null. Okay, that's how that goes. Let's take a look at the last question, and this last question is going to be doing this except using p-values. Now, p-values, when you have z-tables involved, are not that bad. P-values, when you have when you're using t-distribution, is a pain because the p-values are squeezed between two intervals, and it's just kind of between an interval rather between a lower and upper bound, and that those type of questions, we had that in a previous section, but I did say that I wouldn't ask a test question that asked for a p-value that made you look at a t-table because of that extra complication, which could also be we could also overcome by just grabbing a calculator. But anyhow, I'm just not going to ask that particular question. I will ask p-value questions. I don't want to mislead. I will ask p-value questions, or you to do this using a p-value method. But I'm not going to, on the test, ask you to do a p-value method that requires you to look up p-values on a t-distribution because of the lack of accuracy, I guess, on the t-distribution tables. Okay, moving forward. A marketing manager for a cell phone company claims that more than 54% of children age 8 to 12 have cell phones. Okay, so here's the claim, right? More than. So that is, now remember, the HO, or the null hypothesis, always has equal sign. So more than, that's going to be the challenging or the challenger or the alternate hypothesis. So our population proportion is going to be equal to 0.54, and the alternate is going to be the population proportion is greater than. So what we're trying to do, so a marketing manager company claims that it's more than 54% for children 8 to 12. that have cell phones in a survey. So now we've got survey information, survey in a survey of 812 children between 8 and 12 by a national consumer group. Says that 471 of them had cell phones. Well, remember that is that criteria we're looking for, and 471 of them have it. So that allows us to make our population proportion. Remember, that's just going to be the kids that have cell phones over the total sample size. And we can go ahead and figure that. And that ends up being, what is that, approximately 0.58. 0.58. So far you can see that the population proportion, we're saying the assumption is that it equals 0.54. We went out and did some sampling, and in this particular sample we've got 0.51. Now our big question is that different enough? Is that far enough away from our assumption of 54%? Is that far enough away to say, nah, this is no good, cross that out and go with this? Or is it close enough to where we just say, nah, we cannot cross this out, so we're not going to have a strong statement that says that this is true, okay? So that's kind of what we're up against here. Let's see, so let's go through that. Get rid of some of this stuff. Let's go through that, and we just do this step by step to answer this question, the first question here. So now we've got our statements. First question is, compute the test statistic. Do not round intermediate values as usual, round to 2 decimal places. Well, we already know that the test statistic has that formula that you could always look up. Where do you look it up? On that sheet of paper that I gave, and I have right there. We look that formula up. We use that formula right here, and that is going to say that z equals, and I'm going to go right to it this time. It's going to be the sample proportion 0.58 minus the population proportion that we see on the null statement, null hypothesis, divided by 0.54, the population on the null, times its complement, which is 1 minus 0.54, which is 0.46, divided by that sample size, which is 812. Of course, that gets square rooted before you take the quotient, okay, or find the quotient rather. Up top, that gives us 0.04. Down below, we're at approximately, after you square root it, 0.017, 490, 321, and so on. And you divide those, and we get 2.28697917. And it's at round to 2 decimal places. So we're going to say z is approximately equal to 2.29. Okay. Now, the next step to find the p-value. Now remember, p-value is, p is for probability, and probability is just the area under the curve. So basically what we're doing is we're taking this z score, we're looking it up, look up on z table, and figure out the area under the curve, right? Because that will be the p-value. So now let's see, I got to remember, do we even talk about, okay, now look at this, alternate hypothesis is greater than, that means, oh, I didn't fill this out, that's why I didn't look at it. That means it is a right-tailed. That means it is a right-tailed test. So we know that a right-tailed test is going to, let's see if I have space, it's going to be really tight. A right-tailed test looks like this, and this is what we're looking for right there. Now, remember, this is the p-value. This is the p-value, and the p-value is the area under this curve that comes from this z-score. And so this z-score, I'm going to go ahead and plot it right here, right? 2.29. Unfortunately, when we look at the z-score on the z-table, it gives us the area to the left. We got to remember this. And I'm looking for a right-tailed test, right? This is a right-tailed test. So what I need is let's make this blue. It's not, just do that. This is what I'm looking for is that p-value, which is just the area under that curve to the right. Okay, and you know that z-tables give us area to the left, so we go 2.29, look it up on our z-table, 2.29. Where's it at? 2.9 is at the end. So 2.29 is right there. So that gives us an area of 0.9890. And of course, to get this p over here, it's just 1 minus 0.9890. And when I subtract that out, I get my p-value, which is equal to 0.011. Okay. Now, what's going on here? Well, what's going on here is that, let's see, what's our next question? Oh, now we got to figure out if we're going to reject or not. So I'm going to draw a picture to kind of get an idea of what's going on with this whole analysis. What's going on here is that we have, of course, we said this is a right-tailed test. Oops, that's getting very sloppy. What we are saying here, now, the level of significance, the alpha, is 0.05, which is, you know, that's sort of a classic statistical saying, hey, if it's anything at 5% or smaller, then that's unusual. That's, you know, so that's kind of a classic thing. So basically what we're doing here, right-tailed test, we're saying that now remember, alpha is area. Wait, is that going to show up, or am I might be on the edge here. Let me move over. Remember, alpha is area under the curve. So we're saying if the area under this curve over here, this p-value, is smaller than 0.05, we are going to reject. And the reason why we're going to reject also is it's further from zero. It's further from what we think it should be at zero, and it's way out here. So this level of significance is 0.05, and what do we get? Well, we got something much smaller than that. We got this little bit right here, which is the p-value, which is 0.011. That's a lot smaller, and that is, in fact, further away from what we think. So we're going to have to do some rejecting here. So since p is less than or equal to 0.5, it's definitely less, we must reject. Oop, it went to eraser mode. We must reject the null hypothesis at a level of 0.05. All right. Now, what kind of statement do you have when you reject? You got a real strong statement. Let's go back to our initial statements that we had so we kind of see how this works. Remember, we said that the null hypothesis on that initial was that the population proportion is assumed to be 54%, and our alternate is, we think, or that whoever it was, I think it was like a marketing person. Anyways, they said, marketing person says, I think the population proportion is greater than 51% or 0.54. We ran our test. We ran our sampling data, sample proportion. We ran our analysis, and it turns out the p-value is much smaller than our level of significance. So what are we going to do? We're going to reject that assumption because, you know, our sampling data should land close to zero on the z, right, on the z score on the standard normal curve. It's landing much further. It's landing way out here at this 1 percentile, right? Or one, not 1 percentile, that's wrong. 1% of the data to the right. Because of that, we're rejecting the null, and that means we can say this. So we can now have a strong statement. At the alpha of 0.05 level of significance, there is enough evidence to conclude that, and then we want to say this. What is that? More or greater than. There is enough evidence to conclude that more, and that more coincides with that greater than symbol, more than 54, there it is, 54% of the children age 8 to 12 have cell phones. And so that's, anytime we reject the null, we have a nice strong statement. And what's the statement? You just restate that using the language of the problem. In this case, 54% of children age 8 to 12, and they have more. So that's how it goes. If you do not reject the null statement, then it's this wishy-washy. There is not enough information to make that statement. Okay, I hope that helped out. I'm going to also do another video today. Just have to crack it out, and it takes a little time to make these worksheets and cut them up and make them work so I can write on it and turn it into PDF, and then turn it into this notability file, and anyways, all this stuff. So hopefully this is helping out. Guys, stay strong, keep on rolling, and this is 9-4. I'll have 11-1 for you also today, and keep on going. Take care. Have a good day.